Hello friends, this is Abhijat Srivastava. I'm MSc Mathematics, a custom officer, mathemaniac and a blogger. I just love to teach mathematics. In this video, I'm going to teach you the graphical representation of complex number. There are some graphs and curves and you will get all about complex number. And it will be very easy for you to solve many complex problems. And in many instances, you will be able to see the answer directly without solving it. So a complex number is a number of the form x plus iy. This is very correct definition of complex number where x, y belongs to real number. And I is a non-real number. I is not a real number given by I square is equal to -1. As you are aware, any real number, whether it is rational or irrational, can be represented on a line, and the line is called real number line. So a real number line is shown as x-axis here. Imagine a number I whose square is negative and equal to -1. Since there exists no such real number whose square is -1 or negative, consider the equation x square plus 1 is equal to 0. This equation has no solution in real number system, but in complex number system this equation has a solution for x is equal to I. So I is the number whose square is -1, and we can say I is an imaginary number. Since we cannot find any imaginary number on the real line, so for purely imaginary number we need a different line. We represent the imaginary line on y-axis as it is perpendicular to the x-axis, and so it is independent from the real axis. The whole plane is called Argand plane. Since z is equal to x plus iy, that is, any complex number has two components. First is x component, that is real component, and second is y component, that is imaginary component. If the real component, that is x is equal to 0, the complex number is purely imaginary and lies on y-axis. And if the imaginary component, that is y is equal to 0, the complex number is purely real and lies on x-axis. That example is 2. You can write 2 as 2 plus 0i, that is the imaginary component is 0 here, and the real component is 2. It is purely real number, and so it lies on x-axis. Remember, it is incorrect to think that imaginary number are imaginary in the sense they are mathematically invalid. The only meaning that should be attached to the word imaginary is that imaginary number are that number which fall outside the set of real numbers. So complex number z is equal to x plus I, where x, y belongs to R as two parts, real part x, imaginary part y. We can say that x represent the displacement along x-axis and iy represent the displacement along y-axis. So every real number can be written in the form of complex number by association of 0 in the imaginary part. For example, 2 is equal to 2 plus 0, as I already told you. Therefore, system of complex number is extended set of system of real number, as complex number contain both real and imaginary numbers. So real number is a subset of complex number, and complex number is the extended set of real number. Since x square plus 4 has is equal to 0 has no solution on the real number system, so there is need to extend the real number system, and so the system of complex number came into existence. A complex number is called purely real if its imaginary part is 0, that is, if z is equal to x plus iy, z is purely real if imaginary z is equal to y is equal to 0. Similarly, purely imaginary if real part of z, that is x is equal to 0. Representation of complex numbers. There are three types of representation: Cartesian or coordinate representation, vector representation, and polar representation. If one really wants to attain deep mastery in complex number, one should always think of a complex number z is equal to x plus y iy as a point or as a vector. Really important, as a point or as a vector whose x component is x and y component is y. Here is the representation z as a point and z as a vector. Note that when we think z as a point, then it has a fixed location in the plane. It has a fixed location in the plane. Whereas if we think of z as a vector, it is a free entity. Vector, it is a free entity. We can move around the plane as we wish, as long as we don't alter the direction and magnitude. So here you can see the modulus and argument of a complex number as a point and as a vector. You can see the difference. Z as a point. When you take Z as a point, the distance of the point Z from the origin is the modulus of the complex number. That is, this length is the modulus of the complex number. When you consider Z as a vector, the length of the vector Z is the modulus of the complex number. And what is the argument of Z? If you take Z as a point, then the angle made by the line joining the origin to the point Z with the positive direction of the x-axis. When you take Z as a vector, the angle made by the vector Z with the positive x direction. This is the argument. The angle made by the vector Z with the positive direction of x-axis is the argument of complex number. Principal argument. You can see that argument has infinite values. As if theta is an argument, 2n pi plus theta will also a valid argument. As if theta, this line makes theta angle from the positive direction of x-axis, then this line also makes 2 and 2 pi plus theta angle from the positive direction of x-axis. So it will be a valid also a valid argument. So 4 pi plus theta is also a valid argument, and so on. Whereas principal argument lies in the interval minus pi to pi. So every complex number has a unique principal argument. For first and second quadrant, if z lies on first and second quadrant, the principal argument will be measured anti-clockwise from positive direction of x-axis. That is positive direction of x-axis. And if z lies on first quadrant, we measure the angle anti-clockwise, second quadrant for anti-clockwise, and so for first and second quadrant the argument lies between 0 to pi, and for third and fourth quadrant the argument lies between 0 to minus pi, as we measure the angle with clockwise direction. For third and fourth quadrant, the angle is in negative. We take anti-clockwise direction is positive direction, and clockwise direction is negative direction. Remember that the principal argument lies in the interval minus pi to pi, that is open at minus pi and close at pi. Open at pi minus at minus pi means we do not consider the value minus pi in the principal argument interval, and pi close on at pi means that we will include pi as an principal argument. So you can see that the negative x-axis makes minus pi angle and pi angle both, but we take pi as valid argument of negative x-axis, as principal argument interval is between minus pi and pi, and it includes pi but doesn't include minus pi. Okay, so for third and fourth quadrant the principal argument will be measured clockwise from the positive direction of x-axis and the values are negative. A distinction must be made between argument and principal argument. Thus, the argument of a complex number can numerically has infinite values, as 2n pi plus theta is also argument, 2 pi, 4 pi plus theta, 6 pi plus theta, all corresponding to one direction, whereas principal argument gives a particular value for argument, that is helps in assigning the unique argument to a particular z. The polar form. There are two interchangeable notations of any complex number z. If we think z as a point in the plane, we can uniquely determine the location either by assigning its coordinates or specifying its modulus and argument polar form. We need two quantities to specify uh, any point in in a plane, because plane is two dimension. So either we take the coordinate z as a coordinate, that is xy, or we take z as r theta, where r is the modulus of the complex number, that is the length of the line joining the point and the origin, and theta is the argument of the complex number, that is the line OP makes with the positive direction of x-axis. So z is equal to r theta is a polar form. Polar form leads to the Euler form, z is equal to r e I theta. Since z is equal to x plus iy, and you can write x is equal to mod z cos theta, the x component, and y is equal to mod z sin theta, that the y component. So you can write any complex number z is equal to mod z cos theta plus I sin theta, and ei theta is equal to cos theta plus sin theta. If you put the expansions of cos theta and sin theta, you will get the expansion of ei theta, and so ei theta is equal to cos theta plus I sin theta. Conjugate of complex number. If there is a complex number z is equal to x plus iy or re की power I theta, the conjugate will be z bar. The conjugate is represented by z bar, and it will be z bar is equal to x minus iy or re की power minus I theta, that is replace I to minus I. Simple. So if z is equal to x plus iy is a complex number, so then we have to find the location of the conjugate of complex number. If there is a z, that is x, and this is y component, that is displacement along x axis, that is x, and displacement along y axis, that is y. So z bar is x and minus y, that is displacement along y-axis is minus y, so the coordinate is x minus y, and the location of z bar is the reflection of z about the x-axis, or we can say that if there is theta angle, so the argument of conjugate is minus theta, as you can see here, that rei theta is if there is complex number z is equal to rei theta, then is conjugate z bar is equal to re minus I theta, that is now the argument is minus theta. And what is minus z? Minus z is simply minus x minus iy. So displacement along x-axis is minus x, and along y-axis is minus y. So minus z is reflection of z about the origin. Here you can see the addition of complex number. You can simply add two complex number by adding their components separately, or by you can use the addition of vector addition by parallelogram law or subtraction. I think I'm out of time, and thank you for watching this.